So we're going to have a look at another video in energetics, and this time we're going to look at Hess's law and how we use Hess's law to calculate the enthalpy change in a reaction. So first of all, for recap, we have looked at how we use our Q equals mc delta T calculations to calculate an enthalpy change of reactions occurring in solution, or the enthalpy of combustion calculations that we looked at. We've looked at how to use bond enthalpies, bonds energy in to break bonds, energy out when bonds are being made in the last video. And we're going to look at how to use Hess's law now. So Hess's law, first of all, we have to know our definitions for this, obviously, and we need to be very aware of our definitions for the enthalpy changes that we have spoken about in class and that we spoke about in the video for Q equals mc delta T. So first of all, the definition of Hess's law is that the enthalpy change of a reaction is independent of the route taken, provided the initial and the final conditions, I've just written, if the conditions remain the same. So what does that mean, and when would we use it? Well, we use it when we come across particular reactions that are just impossible to follow in the lab. So perhaps they're too quick, perhaps they're too slow, too explosive, perhaps no matter how hard we try to get MB to react to make C and D, we also make certain side products which are just unavoidable. Combustion reactions would be a typical example there, where you pretty much always make some carbon monoxide as well, so if we're looking to try and measure enthalpy of combustion reactions. So there are reactions essentially that we just, for whatever reason, cannot follow in the lab. So we're trying to look at A plus B to go to C plus D, and for whatever reason we simply can't follow it. But we do know, or can measure, the energy change to go from A to B to E and F, and we can measure an energy change to turn E and F into G and H, and we can measure an energy change to go G and H into C and D. So in these instances we can now apply Hess's law to this situation, because instead of going delta H1 route, we are going from A and B to C and D, but via an alternate route. So provided the initial and final conditions remain the same, the overall energy change should be the same. So in other words, delta H1 will equal delta H2 plus delta H3 plus delta H4. Now, it is important that these arrows go in the right direction. They will depend on what information the examiner gives us. And these are just like, no different than this arrow. They go in the direction to illustrate the energy change depending on the information we're given in the question. Now, provided all the arrows are going in the direction we want, i.e. from A and B to C and D, we add them. If you come across an arrow which, let's say, is going in the opposite direction to where you want to go, in that instance you take it away. So that's the equation we turn from delta H1 equals delta H2 plus delta H3 to now minus delta H4. And the same would apply for any of the other ones. If we were given in the question or in the information instead of E and F going to G and H, we were given G and H going to E and F, it would become minus delta H3. Okay, and that's probably what will happen. It's unlikely that the examiner will give you all the arrows and all the information going in the direction from A and B to C and D that you would like. Okay, you may get one. Okay, but it's also really important that whenever you're working out your intermediates down here, okay, that you put your arrows in correctly as per the definitions that you've learned in class. And we'll have a look at some ways to work out what our intermediates are and what direction the arrows go on. Okay, so the first thing that you always do whenever you're working out Hess's law, okay, is you write out and you balance the equation for the reaction that you have been asked to study. Okay, so that is the very first thing, and you must do that every single time. Get that reaction, okay, write it out, and then you can start building your Hess's law cycle from there, because if you don't have that reaction, you really can't build a Hess's law cycle around it. So, in this question we've been asked to calculate the enthalpy, delta H, the enthalpy of combustion of butanol. So the first thing we do is we write out and we balance the equation for the enthalpy of combustion of butanol. So here you have to know your definition for enthalpy of combustion first of all, and that it's the enthalpy change when you burn 1 mole of something in excess oxygen. In this case you'd make carbon dioxide and water. If you don't know that definition, you're not going to be able to even start the question. Right, the examiner has given us over here enthalpy of formation, that's an F. Enthalpy of formation data for those. A lot of people will go, well, I'm trying to work out enthalpy of combustion. Why have they given me enthalpy of formation? Well, they can't give you enthalpy of combustion data, because if they did, they would have to give you the answer. Okay, so let's see how we actually do use this, okay, to work out this. Right, so again we have to know our definition. Well, what is the definition for enthalpy of formation? Well, it's the enthalpy change when you make 1 mole of something from its elements in their standard states. So in other words, they're telling us here how much energy is needed to make a mole of this from its elements in its standard states. Well, what's it made up from? It's made up from 4 carbons in their standard states are solid. It's made up from 5 H2 in their standard states are diatomic hydrogen, and it's made up from a half of an oxygen, which of course is diatomic also in its standard state. So what they're saying here is that the enthalpy of formation of this is minus 327 kilojoules. So which direction should my, so there's my link between this side and this side. Okay, they're then telling me that to make a mole of carbon dioxide is minus 394. I make carbon dioxide from these as well, not the hydrogen obviously, but the carbon dioxide. So 394. Okay, and my water, to make water, is minus 286. Again, enthalpy of formation from its elements in their standard states. So we've now, and this is really important, that if you know your definition for formation, you put your arrows to illustrate the direction in which the definition tells you to go. So it's formation, so we are making that. And that comes out at minus 327. Okay, we're only making it, this is kilojoules per 1 mole, I haven't written it on here, but just well, kilojoules per 1 mole. Okay, so we're making 1 mole of it. Okay, it's nothing to do with these numbers down here, we're making 1 mole of that, so it's minus 327. Over here we're making, so the arrow's got to go towards making, formation of carbon dioxide, that's minus, but it's, we're making 4 of them, 394, 4 of them. And we're making, again, enthalpy formation, water, we're making 5 of them, so it's 5 upon minus 286. Now, so that's the energy change that we're trying to work out here. We've been given this information, we've worked out what our link is between left hand side and right hand side. Okay. We have put our numbers on, our arrows in the right order, because if our arrows don't go in the correct direction, we'll end up taking away something that we should be adding, and vice versa. And we've got everything in here all balanced, state symbols on correctly, anything that's diatomic is diatomic, and if we were asked to construct the Hess's law cycle for this, hopefully we would get full marks. Now we've got to do our calculation. Well, this is going in the wrong direction, because what we want is we want to start here and go to there. So the red arrow on the left is going in the wrong direction, so our delta H will equal 4 upon minus 394 plus 5 upon minus 286. Remember we said we add any arrows that are going in the right direction that we want to go, and then here we take this away, so that is minus 327. Could have just added 327 either way, so let's do that. So it's 4 upon minus 394 plus 5 upon minus 286 plus 327 gives us, do that again, 394 plus 5 multiplied by minus 286 plus 327 equals minus 2679, and that is units of kilojoules per 1 mole. And I asked myself, well, does that seem sensible? Yeah, well, I'm burning an alcohol here, so I would expect to get an exothermic, and really quite an exothermic reaction. Okay, so there you go. That's how you would go about a Hess's law cycle, one of them anyway, in terms of constructing it based on the information given to you, okay, and where you start. So we'll do another couple. Again, you can pause the video, and when I write the question out, you can have a go at it yourself, but there's plenty in your notes for you to have a go at also. Okay, so this time what we've been asked to do is calculate the enthalpy of reaction for photosynthesis reaction. So again, we write out the equation, that's our starting point, and we make sure that it is balanced, which I think it is, okay? No, it isn't. It is now. Alright, that's a 6. Okay, so we have, again, we've been given enthalpies of formation, so the energy to make a mole of that, a mole of that, and a mole of that. So what do we make them all from? They're elements, of course, in their standard states. So 6 carbon solid. Okay, we will need 6 hydrogens gas, and we will need 6 O2. We will need 9 O2 gas. Okay, right. So that, if we were to do a Hess's law, we get our arrows in now, but that would be our marks picked up for actually doing the Hess's law cycle. Right, let's put our arrows in then. So we are enthalpy of formation. We are making carbon dioxide, so we're going towards the carbon dioxide. We are making water. We're going towards the water, and we are making the glucose sugar. So in that direction. Okay, so our arrows are going in the right direction. Let's now put, some of you might say, well, why is there no oxygen here? Why no enthalpy formation of oxygen? Well, enthalpy formation is defined as the energy needed to make 1 mole of a substance from its elements in their standard states. So that would be oxygen O2 gas to O2 gas. Well, that is a 0 kilojoules energy change. So there is never, you will not see an enthalpy change for an element because there is no value associated with it. Okay, so let's look at our carbon dioxide, and we are making 6 carbon dioxides, so we have minus 394 times 6. We are making 6 waters, so we are minus 286 times 6, and we're making 1 molecule of glucose, which is minus 1273. So our delta H for photosynthesis is minus 1273. Okay, this is going against us. We want to go from here to there, so that arrow is going against us, so we take that away. So that is minus minus 286 times our 6, and then the same here. That is, take that away. So that is minus 394. Multiplied by our 6, so we'll just plug those into my calculator here. And it is photosynthesis. Okay, so we should be sort of thinking along the lines, is this going to be exothermic or endothermic? Okay, and it comes out at positive 2807. So it's taking in energy, and you would probably expect that from it's per mole of the glucose in this instance. Okay, so I've done a couple there, guys. Hopefully gets the concept across to you about how to do the calculations and how to draw them. We'll do a couple now where we, instead of being given enthalpy of formation, we're given enthalpy of combustion information, and we'll see how those go, and then you guys can go and have a few in your own. Okay, Okay, so this time we've been asked to calculate the delta HF, the enthalpy formation of C4H10. So we've got to write the equation, like I always say, write the equation. And this is a bit odd because people find very often that the wrong answer we'll get will have this on the left hand side of the arrow down here. But enthalpy of formation is the enthalpy change when you make 1 mole of something from its elements in the standard state. So this time that's got to go there, and that's a wee bit counterintuitive, but nonetheless that's what has to happen. Okay, we've got 4 carbons which are solid. Hydrogen is diatomic and a gas, and we need 5 of them. So this time we've been given enthalpies of combustion of these things. So this is our link. So if I burn this, I get carbon dioxide. If I burn this, I get water. And if I burn this, I get carbon dioxide and water. So there's my link. Carbon dioxide and water, carbon dioxide and water. Linking the left hand side to right hand side. Now what we've got to do is put our arrows in correct direction. So this is enthalpy of combustion, and its definition, it's the enthalpy change when you burn 1 mole of something in excess oxygen. So I'm burning that, and I'm going to that, and I'm burning that, and I'm going to that. Now we need to put our values on and multiply up if need be. Well, these remember are always kilojoules, moles to the minus 1. So when I burn 1 mole of that, I get minus 2876.5 kilojoules, and it is only 1 mole of it being burnt. Carbon, when I burn that, I get minus 393.5, but I'm getting 4 moles of it. I'm burning 4 moles of it, sorry, so it's 4 times that. And hydrogen, when I burn 1 mole, I get minus 285.8, but I'm burning 5 moles of it. So again, my calculation, this is the delta H that I'm after, so delta H equals minus 393.5 times 4. This arrow is going in the direction I want them to go in, so is this one, so it's plus it, minus 285.8 times 5. This arrow is going in the opposite direction, so we add that, so plus minus 2876.5, and we'll do that calculation, see what we get. So minus 393.4 plus 28. So I'm ending up with a value of minus 5879.5. Okay. Just going to double check, that looks very high. Minus 3. Yeah, sorry, made a mistake there. I had a plus arrow there, that should have been a negative. Okay, once I sorted that out, the answer was minus. So, good exercise there, guys, that I got an answer of minus 5,000 kilojoules, and I thought immediately I'd done something wrong there. Okay, I went back and checked, found there was my mistake. Okay, so again, just a lesson to all of us. Be careful from that point of view. If you get a strange looking answer, don't always trust your calculator. Right, I'm going to move on to do one more, and then that'll be me. This time it is to calculate the question is to calculate the delta HF of ethanoic acid, and again my compounds are, or my substances are, I should say, they're not all compounds, carbon, hydrogen and ethanoic acid itself. And again, they've given us this time delta HC, so we've done 2 enthalpies of where we've been given enthalpy of formation, and 2 where we've been given enthalpies of combustion. So again, the first thing is I read out my equation, and we have, because it's enthalpy of formation of ethanoic acid, my ethanoic acid has to be on the right hand side, and my elements, or its elements if you like, on the other side. Okay, so we have 2 hydrogen diatomic, and we have O2 diatomic. Again, you'll not see enthalpy of combustion of oxygen here, because when you combust something you react it with oxygen, and hopefully you're able to work out why that would not be an enthalpy change. So enthalpy of combustion of values of these, I'll just write them in, minus 393, minus 286, and minus 487, all negative of course, because your enthalpies of combustion all exothermic. So if I burn carbon, I get carbon dioxide. If I burn hydrogen, I get water, and if I burn this, I get carbon dioxide and water. So there you go, there's my link between the left hand side, carbon dioxide and water, and the right hand side, carbon dioxide and water. So the next thing we're going to do is put in our arrows as per the definition. So combustion is towards the combustion products. Okay, and then we put our values in. So when I combust 1 mole of carbon, it is 393, minus 393, sorry. So, but that's 2 of them being combusted. When I combust hydrogen, that's minus 286. Again, we are combusting 2 of them. Okay, and when I combust carboxylic acid, ethanoic acid, sorry, is minus 487 kilojoules of energy. Okay, so this one is going with me, this one is going with me, and this one is going against me. So let's do my delta H, which is what I'm trying to calculate, equals minus 393 times 2, okay, plus minus 286 times 2, and then this is the one that's going against me, so it will be, take that away, so it'll be minus or plus that, and if we do that all, we will get an enthalpy change of positive 53 kilojoules per mole. Okay, so hopefully that gives you a bit more of an enlightenment into Hess's law, how to do them, how to do the calculations. Obviously knowing your definitions here is key. Most of the ones that I've done there, they don't vary too much away from the standard one for AS level chemistry. There are other ones which are a wee bit more challenging that you probably want to do as well, but they're really just applying the principles that I have done in this video. Okay, hope that helps, guys.